So last time we have discussed a non-uniform oscillator and a time period for non-uniform oscillator. So that lecture one correction is the section is not 4.2, that's 4.3. Okay, so and the time period for that non-uniform oscillator, what we have got is in this form, right? Before going to the next method to solve the time period, okay, what we are going to do is we are going to do a little analysis on this equation. So first let's plot it. So if we plot it, okay, where this is my a axis and this is my omega, sorry, not omega, time period, then this is the graph I am going to get. Okay, so this graph, if we see, when my a value is 0, then it has a time period which is something, and that value is equal to 2 pi by omega. Okay, so like a uniform oscillator. But as a increases, what's happening to the time period? The time period is increasing and it's almost goes to, not almost, it goes to infinite. When it goes to infinite, when my a approaches omega. Okay, so when my a approaches omega, then this value, the time period, goes to infinite, which means there won't be any oscillation. That's what the time period goes to infinite means. Okay, so this a is something like which is arresting the oscillation, or yeah, we could say, we could understand this factor a is something which slows down and resisting the oscillation. Okay, so that's the factor a. Okay, fine, let's and also if you remember, we have seen that this equation at omega approaches, so let's write it like this. When the value a, right, approaches omega, let's call omega minus, because what we are considering is a is less than omega, right? So when it's approaching from the lower side of omega, then this value, the time period, approaches a value which is pi root 2 by root omega into 1 by root omega minus a, right? And this is known as square root scaling law. Okay, and in this video we will see why it's been called a square root scaling law. So we are going to do that for this case. Okay, so right, so first let's see theta dot versus theta when omega, when a is very near to omega. Okay, so let's plot it. Okay, let's reduce it so that okay, so a is very near to omega, only slightly this omega is large. Okay, At that time what will happen is it will have an oscillation, okay, it will have an oscillation, but the thing is when it crosses here it will take a very long time, okay. So it will take a very long time, and it looks like compared to the time taken to cross these regions are almost negligible compared to the time taken for crossing this region. Okay. So it looks like it will be moving very fast and suddenly it will almost stop, okay. It will slowly move and then once again fast, okay. So therefore what we could do is the time taken for crossing this region is going to have most contribution in time period for such a system, okay. So we are going to use that idea in order to calculate the time period, okay. And one more thing, here we have observed that when omega is getting decreased, then two fixed points appear, okay, from the situation where no fixed points. So this is a behavior of bifurcation, and this bifurcation is known as saddle node bifurcation, okay. So we are going to use the normal form of saddle node bifurcation and we are going to solve it. So what we are going to do is the following. So we are going to consider the system in the flow in the line, okay, which is x dot is equal to r plus omega square, sorry, not omega square, x square. So that's the normal form, right? And if we plot the normal form, what we will get? We will get a parabola, right? Let's plot it, okay. We will get a parabola which will be, let's say y is equal to, for r let me put a very small number, plus x square, okay. So that's a parabola. Now if you see again, once again, if I try to calculate, I mean there is no fixed point. Since there is no fixed point, if I start from minus infinite, okay, for the x value, then it will keep on increasing and it will reach infinite, okay. But the thing is, what is the time taken for x to reach from minus infinity to infinity? That actually could have some value, but if we could calculate most of the contribution that time taken from to go the to take the x value from minus infinity to infinity will have the large amount of time will be spent to cross this region, okay. Therefore what we are going to do is, whatever the time taken for this system to go from minus infinity to infinity, that is going to be the time taken for crossing this region, okay, crossing this region, okay. So using that idea, we are going to calculate time period when we have such a situation, okay. Let's do that. So this is my normal form for saddle node bifurcation, and the time period, which is integral of dt, which is equal to integral of, from where to where, from minus infinity to infinity dt x by x dot. Okay, and for this, if I calculate, if I substitute this for the x dot, I'll get integral of minus infinity to infinity dx by r plus x square. And if you do the calculation, what you will get is the following. Pi by root r. Okay, and this is the reason we call the time period is a square root scaling law. Okay, and okay, so here we have omega minus a, but here we have root of r. But what is this r represents in this system, right? For that, what we have to do is we have to write this function, the function which we are dealing, theta dot is equal to omega minus a sine theta, into a normal form. Okay, we have to approximate this form into a normal form, which is this one. Okay, once we do that, we will be able to understand what is the meaning of r for this system. Okay, and if we I'll leave that as an exercise, but and if we calculate, what we will get is the following, which is r is equal to omega minus a. Okay, right, and if we substitute, what do we get? I got a little confusion. Maybe if I substitute over here, I'll be able to get this term. Okay, maybe in the next video I will try to clear that one.